Okay, let's get started. Welcome, everyone. We will come back to this problem, as usual, later on in class. I realize that last class we didn't do that, but that's because we ran out of time, and we will cover that problem in this class too. So starting out with some course announcements. As I hope you are all aware, problem set 1 is due today at 11:59 p.m. Montreal time. Please submit that via my courses if you have access, otherwise by email to me and Vincent. Clarification on problem 2. With irrational numbers, please don't simply cite the fact that square root of 3 is irrational. Unless you are going to prove that, which is totally fine. If you prove it, that is not a problem. Just that will be an example of something which sort of trivializes the problem. So if you just cite that and say it is known that this is the case, that would not be a full proof. Are there any questions about the problem set or in general about the class? Okay, well, if you have any questions or issues, please do ask later or message me in the Slack. Great. So let's start out by finishing up some stuff from last class. So last class was on polynomials and algebra. Now we're going to cover the final component of that, which is inequalities. And this is an entire large subject thinking about looking at inequalities and solving them. So this is only going to be a little bit of that, just a couple of slides, just to give you a taste of this area. So the sort of most trivial inequality that you might end up using in practice is called the trivial inequality. The inequality that is very easy to prove. And that is that the square of anything is positive. And this is something that I think we've all seen probably intuitively. So for any real number, the square is non-negative. This is surprisingly useful for something that is very simple. It will turn up a lot, and it will turn up in non-trivial situations. Here's an example of one way you might use it. Why does this polynomial, x squared minus 2x plus 2, have no real solutions? Well, if you plug in any real number, you can do some kind of factorization here. You can say, oh, look, well, x squared minus 2x plus 2 is very similar to x squared minus 2x plus 1. And if you've seen that before, you might recognize that that is x minus 1 squared. And so this whole thing is x minus 1 squared plus 1, which means that the entire thing should be greater than or equal to 1 if x is a real number. So that is a very swift proof that there are no real solutions, no real roots to this polynomial. You could also use the quadratic formula to show that it has complex roots, but this is maybe a little bit faster. A slightly more sophisticated inequality, which comes up again and again and again, is called AMGM, the AMGM inequality, which stands for arithmetic mean, geometric mean. And it'll be clear in a few moments why that is the case. So the two variable case of AMGM is that a plus b over 2, so the average of a and b, is greater than or equal to the square root of ab. And this is the case only for non-negative ab. So ab greater than or equal to 0. The thing on the left is the average, or the arithmetic mean of a and b. The thing on the right is called the geometric mean. It's what happens if you take the average, but you're taking the average in a sort of product way instead of taking the average in an addition way. So it's like the multiplication version of the arithmetic mean. And you can relate the two also if you want to use logarithms or something. But yeah, so this is the two variable case. The more general case is, again, that the average, or the arithmetic mean of n different non-negative variables is going to be greater than or equal to the geometric mean of those variables, where we have the geometric mean being the nth root of the product of them if there are n of them. So if you had 3 variables, it would be the cube root of the product of all 3. No. I'm not going to prove the entire theorem here, the entire AMG inequality, because it's not that fast to prove. You can certainly find a proof and understand it, but let me just prove the 2-variable case here. So how would one go about doing that? Well, you could just square it. Since you have the square root, something you might naturally do is try squaring both sides. And if you square both sides, you get something that is equivalent because both sides are positive. So if this is true, then you can take the square root of both sides and have it still be true. So they are equivalent statements. Each one implies the other. In the square, you have a squared plus 2ab plus b squared over 4 is greater than or equal to ab. Now, what can you do with this? How could you prove that that is the case? If you could prove that's the case, then you could take the square root of both sides and prove that AMGM is true. Yes, you can multiply by 4. And what would happen after you multiply by 4? It's a bit of rearrangement you could do. Yeah. So if you multiply out and then you rearrange, you get a squared minus 2ab plus b squared is greater than or equal to 0. And that, as some people are commenting, is just the trivial inequality, which is a minus b squared is greater than or equal to 0. So the trivial inequality is not that trivial. It actually lets you prove AMGM, which will turn up a lot. Okay. Let's take a look at this problem. Before we get to this problem, can the general case be proved by induction is a question. Yes, the general case can be proved by induction, but maybe not in exactly the way you think. I would encourage you to take a look at different proofs of AMGM, and the induction is not the kind of induction quite that we have done here. It's the same kind of induction, but it's a more complicated induction step. You could also use Jensen's inequality and convexity and stuff, if you have seen that. Okay, so the problem that we never got to last time. What is the minimum possible value of x to the power 100 plus 3 over x to the power 100? What can we do? So we could use calculus, as a couple of people are suggesting, and that would absolutely work. There is a faster way and maybe a nicer way. So we'd like to find the minimum possible value. So we'd like to show that this is greater than or equal to something. There's a suggestion to factor this according to the formulas from the last lecture. We absolutely could try to do that, at least. It would be a little bit difficult because it's the sum of 2 squares, not the product of 2 squares, but we could do it. We would have some complex numbers in there. I'm not sure that it would immediately help us, but there's also something we can do which is more simple. Somebody's noticed that the product of the 2 terms is 3. So we have the sum of 2 things, and we know what their product is. And the product is a constant. So, as some people are suggesting, we can use AMGM. So we know that the average of any two numbers is at least the geometric mean of those two numbers. So if we divided this by 2, we know it would be greater than or equal to the square root of the product. But the square root of the product is actually really simple. It's just square root of 3. Which means that if we multiply by 2, we get that this thing which we wanted is greater than or equal to 2 times the square root of 3. And that's it. We're done. Now, we're not totally done. I'm glossing over one small thing here. We need to know that it's possible. So we do need to check that this value is actually attained at some x. And I didn't talk about this on the previous slide, but AMGM has what's called an equality case. I'll put it in the slides when I post the slides. But the equality case just says that if all of the things that you're averaging together are the same, then AMGM holds with this being an equality instead of an inequality. So if x to the 100 is equal to 3 over x to the 100, then we have equality. And that's possible when you have x equal to the 200th root of 3. Another detail, which I also sort of glossed over, is you can only apply AMGM to positive or non-negative numbers. But these are non-negative because they're 100th powers, and 100th powers are in particular squares, so they're always non-negative by the trivial inequality. Are there any questions about this or any of the inequalities we've just gone through? Why did we multiply by 2 in the end? Because the AMGM inequality says that the average of two numbers is greater than or equal to the square root of their product. And since we weren't looking at the average, we were looking at the sum, we had to divide by 2 to get square root of 3. And so if something divided by 2 is at least square root of 3, then if you don't divide by 2, it's at least 2 times that square root of 3. There's a question about how we would prove this to make sure that we aren't going backwards instead of going forwards. If you were writing a formal proof, you would say, okay, well, because of AMGM, this is true. Therefore, we know that this is greater than or equal to 2 times the square root of 3. Equality is attained here. In the proof of AMGM, we did do a little bit of going backwards, but that part of the proof is reversible, so we could write it forwards. If you didn't catch what I just said there, don't worry. It was just a detail about writing proofs backwards versus forwards. The question about whether something's about the minimal question. So yeah, so the question was, suppose that you say something is greater than something else. For example, I could say, this is greater than or equal to 0. It is true, it's greater than or equal to 0 because each of these things is non-negative. A square is always positive, so a 100th power is always, sorry, a square is always non-negative, so a 100th power is always non-negative. But if I said it's greater than or equal to 0, that would be true, but it wouldn't be very helpful in the sense that 0 is never actually attained. There isn't an x that will give you 0. It's greater than or equal to 0 because it's greater than or equal to 2 times the square root of 3. So the reason why we had to show that this important detail is that we needed to check that there is actually some x that causes this inequality to be equality. However, AMGM will sort of give you that in that the equality condition of AMGM, when this thing is equal, is exactly when if you go back to this previous slide, Equality is attained when all of these things are equal. If all of them are equal, then the arithmetic mean on this left-hand side is equal to just A1, and the geometric mean is also equal to A1. So we're using AMGM, the inequality, to show that it is greater than or equal to 2 times the square root of 3. And we're using AMGM, the equality condition, to show that there is some x that actually satisfies the inequality. So the inequality is in some sense tight. Does that make sense? Is the lower bound 2 times the square root of 3 the tightest lower bound? Yes, because there is some x which satisfies it. That's the point. Equality happens when you set x equal to the 200th root of 3. That's why this is the minimum possible value, because there is some x which gives you 2 times the square root of 3. Is there something which is still confusing about how I'm explaining this? In order to show that you have a tight lower bound, or what the minimum value of something is, you need to show that it's always greater than or equal to that minimum value. And you also need to show that there is some x which attains that minimum value. Otherwise, it's not actually the minimum value, it's just something lower than the minimum value. There's a question about whether AMGM is convex. I'm not sure exactly what you mean by is it convex, since it is an inequality. It relies upon convex functions. Yes. Okay, let's move on. Please message me afterwards if there was anything unclear in what I said. Now we're actually going to do what we were supposed to do today. Sorry for that long digression into inequalities. And that is number theory. So number theory is the area of math that concerns integers or whole numbers. And basically, a lot of number theory rests upon prime numbers. So let's start out with primes. A prime number is a positive integer that is divisible by no positive integers other than itself and 1. The primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. In particular, 1 is not a prime number. That's partly just a definition thing, but we'll see that various things about prime numbers sort of break if you let 1 be a prime. So it's sort of, it's a notational thing, but it's very convenient not to always say primes except for 1. Some cool things about prime numbers. There are a lot of cool things about prime numbers, but here are just a few of them. There are infinitely many primes. We've actually already proven this. That was in the contradiction class. Bertrand's postulate. For every positive integer n, there is a prime between n and 2n. I guess I should have said for every positive integer n greater than 2, greater than 1, there is a prime between n and 2n. This generally doesn't actually come up. It's just something that's cool. Something else that's cool. How many primes are there? So like, how many primes are there that are less than 10 million? Well, the number of primes less than n is approximately n over log n, where log is the natural logarithm, base e. That is actually exact in the limit as n goes to infinity. So as n gets really, really big, the number of primes less than n will be pretty much exactly n over log n. However, actually working out what are primes is still not super easy. You can do it with a computer. In particular, you can just check if they have any factors other than themselves and 1. But there aren't extremely easy ways to work out what the primes are. Even though they have these nice sort of aggregate properties, working out exactly where individual ones are is still hard. So something that we've seen before in class a little bit is the fundamental theorem of arithmetic. And this is saying that every positive integer n greater than 1 can be written uniquely as the product of primes. You can factor it into powers of primes. This is one of the reasons why we don't want 1 to be a prime, because prime factorization would not be unique, because you could include 1 or not include 1, and it wouldn't matter. For example, 36's prime factorization has 2 2's and 2 3's. There are 2 factors of 2 in there and 2 factors of 3. 2 squared times 3 squared equals 36. There is no other way to write this as a product of primes unless you were to shuffle around the 2 and the 3. What happens if the number is a square? For example, 36. Yeah, so the exponents are all going to be even in that case. And in order to work out what the square root of n is, you just divide all of the exponents by 2. So in this particular case, the square root of 36, you divide each of the exponents by 2, and you get 2 times 3, which is 6. Likewise, if n is a cube, then all of the exponents are going to be divisible by 3. And you can just divide them by 3 to get the cube root. Here's a cool problem. Suppose that you have the prime factorization of an integer n. How many positive integer divisors does it have? We have some disagreement in the suggested answers. So far, none of the answers is correct. Let's work it out. Let's see an example. 18 is equal to, the prime factorization of 18 has 1 factor of 2 and 2 factors of 3. The divisors of 18, we can just go through them. There's 1, there's 2, there's 3, 6, 9, and 18. And let's just go through the prime factorizations of them. The first one factors is 1, then 2 to the 1 factor of 2, 1 factor of 3, a factor of 2 and a factor of 3, 2 factors of 3, and then 18 itself. Okay. Maybe that's given us a little bit of a sense of what might be going on here. But let's take a look. Suppose that we have a divisor m of n. First of all, what primes can divide m? What are the possible primes that we have to pick? Like, we already know some primes. Like, there are the primes that are less than n. Yes, there are the primes that are less than n. We've already seen some primes in the factorization of n. Careful, 1 is not a prime. Also, m might not be a prime. Yeah, so the primes that could divide m are the primes that divide n. If there were some other prime, p, that divided m, then it would also have to divide n, because m divides n. And if p goes into m and m goes into n, then p also goes into n. So the only primes that we have to work with are p1 through pk. That's good. That means we can write a prime factorization of m using the same primes as n. Okay, so now all we have to do is work out the exponents. What are some possible exponents, s1 through sk, for m? It might be easier to think about with an example. Like before, we had 2 to the 1 and 3 to the 2. Yeah, this is sort of a combinatorial problem in response to that question. But we're not going to have to use like combinations and permutations or anything like that. Yeah, so as some people are suggesting, we know that each SI is between 0, if that prime just doesn't occur, and R sub I. The maximum that it could be is R sub I. So, going back to our previous example, we could pick, so here we could pick 2 to the 0, 3 to the 1, here. We could pick 2 to the 0, 3 to the 2. We could pick 2 to the 1, 3 to the 2, and so on. So each individual exponent can be between 0 and the max exponent Ri. Since there are Ri plus 1 possibilities for each Si, 0, 1, 2, 3, 4, all the way up to Ri, we have a total of Ri plus 1 for each of the Si's, and those are all independent. So Ri plus 1, the product of all of those, R1 plus 1 times R2 plus 1, all the way times Rk plus 1, different divisors. And that includes the divisor 1. We know that 1 divides n, certainly. And 1 corresponds to the prime factorization where every exponent is 0. So again, going back to our example, the divisors are here 1, where we picked the exponents 0 and 0, 2, where we picked 1 and 0, 3, where we picked 0 and 1, 6, where we picked 1 and 1, 9, where we picked 0 and 2, and 18, where we picked 1 and 2. So in each of these cases, we've picked the same primes and exponents which are less than or equal to the max exponents given by the number n. And so again, the number of divisors is equal to the product of 1 plus the exponents. So 1 plus 1 times 1 plus 2 here. That's going to be 6. Are there any questions? Okay. Just going back to the previous slide in response to a question. Was there something unclear? Thank you so much for telling me when something is unclear. I really appreciate it. It's really hard for me to gauge class reactions, given that I can't see you all physically. So I really rely upon you telling me if I'm going too fast or if there's anything that I didn't explain correctly. So thank you. Okay, if there's anything that's unclear or a problem, let me know afterwards. Okay, LCM and GCD. the least common multiple, which is often called the LCM, and weirdly, it's called the LCM with lowercase letters, traditionally. The least common multiple of two numbers is the smallest integer that is a multiple of them both. I guess I should say the smallest positive integer. So as an example, the least common multiple of 10 and 12 is 60, because 60 is a multiple of both 10 and 12, and there isn't anything smaller than 60 that is a multiple of both 10 and 12. The greatest common divisor, which is called the GCD of two numbers, is the largest integer that divides them both. So as an example, for 10 and 12, the GCD is 2, because 2 divides them both. 1 also divides them both, but 2 is larger than 1. How do LCM and GCD relate to the prime factorization? So in this particular case, those are the prime factorizations of 10 and 12. So there's a lot of talk about union and intersection of prime factorizations. You can try to make that a little bit more rigorous. I can just write this down. Let's expand these factorizations so that they include the same primes. So I included some primes to the power 0. Notice any patterns with the LCM and GCD. Yeah, so as someone has suggested, the LCM, if you look at it, it's going to be, we saw it's 60, and 60 has the prime factorization this. If you look at this, you see that the exponents here are the maximum of all of these. So 2 to the max of the exponents here, 3 to the max of the exponents here, 5 to the max of the exponents here. So in 12, we had 2 to the 2, so we take 2 to the 2, that's the highest power of 2. We also had 3 to the 1, which is the highest power of 3, we take 3 to the 1. 12 doesn't have a factor of 5, but 10 does, and so we take the highest power of 5, 5 to the 1. Similarly for the GCD, which is 2, or 2 to the 1, it's just these primes to the min of the exponents. So here it's the min of the exponents in 10 and 12. If we're going to divide both of them, we need to have the minimum exponent on 2, so 2 to the 1. And since 3 only divides one of them, we can't have a 3. Since 5 only divides one of them, we can't have a 5. Does this make sense? So the LCM is the same primes as the union of both, with the exponents being the max of the exponents between the two. The GCD is the same primes with the exponents being the min of the exponents. And as a comment suggested, this will also allow you to show that the LCM times the GCD is equal to the product of the two numbers. I'll let you work that out, but as you can see, 60 times 2 is 120, which is equal to 10 times 12. Here's a way to work out what the GCD of two numbers is. So to do this, we're going to use the claim that the GCD of two numbers is the same as the GCD of one of the numbers and the difference of the numbers. So why is this true? Well, anything that divides both m and n must divide their difference, m minus n. And conversely, anything that divides both n and m minus n must also divide their sum, which is m. That means that the biggest common divisor of m and n is also the biggest common divisor at n and m minus n, since the divisors of this pair are just the same as the divisors of this pair. The biggest one for these is the biggest one for these as well. Do those claims go both ways? Yes. This is just showing that the claim goes both ways. So let's use this to find the GCD of two big numbers. We know that it's the same as the GCD of the smaller of the two and the difference of these two numbers. That's 42 and 182. Because 42 is just 224 minus 182. Now we can do that again. We take 42, which is the smaller, and the difference of these two, which is 140. Let's do it again. 98 is the difference of these two numbers. 98 and 42. Go from there to 56 and 42, because 56 is 98 minus 42. Go from there to 14 and 42, because 14 is the difference between these two. Then 14 and 28, because 28 is the difference between these two. And then 14 and 14, because 14 is the difference between 28 and 14. So what happens now? Well, you have the GCD of 14 and 14. But the greatest common divisor of 14 and 14 is clearly 14. So that was the GCD of the two original numbers. So this is called the Euclidean algorithm. And this is basically a proof of it. It's one way to find the GCD of two numbers without doing a prime factorization. Relatively prime numbers. Two positive integers are said to be relatively prime if they have no common divisors except for one. So that means that, for example, their GCD is 1 because they have no common divisors at all except for 1. As an example, 6 and 25 are relatively prime, even though neither is actually a prime itself. But they don't share any factors apart from 1. What can we say about the prime factorizations of two relatively prime integers? M and n. Suppose m and n are relatively prime. Yep, the primes are going to be completely different. None of the p's can equal any of the q's. It's just equivalent to them being relatively prime. Okay. Are 1 and 1 relatively prime? I guess. I'm not sure the formal definition of relatively prime as it pertains to 1, but I think that yes, they would be relatively prime. Okay. Now we're going to get started with modular arithmetic, which is a really useful area of number theory. To answer the question, yes, 1 is an exception to many things. So let's get started with a definition. For integers x and y and a positive integer m, we write x is equivalent to y modulo m if x minus y is a multiple of m. And I'm going to say, so you can describe this in various different ways. I'm going to say x equals y modulo m. You can also say x is congruent to y modulo m. That symbol in LaTeX is \equiv, for what it's worth, for an equivalence relation. So some examples of this. 12 and 62 are the same modulo 10. Because their difference is just a multiple of 10. In the case of 10, you can work this out pretty easily by looking at the last digit. Though, you should also be aware that 12 is also equal to -8 modulo 10. That's because -8 and 12, the difference between them is 20, which is a multiple of 10. So once you go to negative numbers, all the negative numbers congruent to 12 will be ending in 8. Now, every integer is going to be equal to one of the integers 0 through m-1 modulo m. For example, 17 modulo 5 is 2. That is called the quadratic residue of, sorry, no quadratic. That is called the residue of x modulo m. Likewise, -3 has residue 2 modulo 5. That's because 2 and -3 differ by a multiple of 5. In this case, they differ by actually 5. And you can think of this as the remainder when dividing by m. So 17, if you divide by 5, you have a remainder of 2. 2 is left over. So if you have to pick a single number to represent an integer modulo 5, you pick one of the residues, so 0 through 4. In particular, anything that's actually divisible by m is going to have residue 0 modulo m. So 5 has residues, 5 is equal to 0 modulo 5. Now here's something that is very useful. Addition and subtraction work modulo m. This is not to be taken for granted, but it's really nice that they work. In particular, if you have x congruent to a mod m and y congruent to b mod m, then x plus y is congruent to a plus b mod m. And the differences are also congruent. Why is this true? Well, let's suppose that x and a are congruent mod m and y and b are congruent mod m. That means that we can write x equals a plus some multiple of m and y equals b plus some multiple of m for some integers c and d. It's multiples of m. And that means that the sum can be written as a plus b plus c times m plus d times m. And if you rearrange it, you can see the multiples of m sort of go together, and you get a plus b plus some multiple of m. That means, by definition, that x plus y is congruent to a plus b modulo m. And likewise with the differences. X minus y equals a minus b plus some multiple of m, so it's congruent to a minus b mod m. Oops. Any questions so far? Okay. Let's see some examples. 61 plus 16, if we reduce this mod 2, 61 is equal to 1 mod 2. There are only two possible residues, modulo 2, 0, and 1. 61 is odd, so it's 1 mod 2. 16 is even, so it's 0 mod 2. Their sum, an odd plus an even, is equal to an odd. And that's just 1 plus 0 equals 1 mod 2. Likewise, a difference. 14 is equal to 2 mod 3. And 5 is also equal to 2 mod 3. They're both 2 more than a multiple of 3. So 2 minus 2 is equal to 0 mod 3, divisible by 3. Multiplication. Multiplication also works really nicely. If two things are equal mod m, then you can multiply them by any integer and they're still equal. Why is this true? Well, for a similar reason. If you have two things that are equal mod m, then their difference is a multiple of m. But that means that the difference of ax and ay is a times that same multiple of m, and that's also a multiple of m. And that means that ax and ay are also congruent modulo m. As an example, you have 12 is equal to 2 mod 10, and if you multiply both sides by 3, you get 36 is equal to 6 mod 10. As another example, which is a little bit more subtle, 4 is congruent to -1 mod 5. And that means that 4 to the n is congruent to -1 to the n mod 5. Because we know that multiplying by 4 is the same as multiplying by -1. So if you just do it many times, 4 to the n is equal to -1 to the n. But that means that we can easily show that all the powers of 4 alternate between -1 and 1 mod 5, as indeed they do. 4, 16, 64, 256, and so on are -1, 1, -1, 1 mod 5. And we see this nice repeating pattern. Here's a problem. Prove that a positive integer is divisible by 9 if and only if the sum of its digits is divisible by 9. This is the standard divisibility rule for proving that something is divisible by 9. So for example, 81 is divisible by 9 because 8 plus 1 is 9. Why is this true? So let's start out by writing the integer x in terms of its digits. So we know that x can be written as, this is just the representation of x in base 10. 10 to the n times the nth digit plus 10 to the n minus 1 times the n minus first digit, and so on all the way down to the 0th digit. Great. What can we do here? How can we simplify this? Whenever you see something like divisible by 9, you should think of mod 9. Because something is divisible by 9 if it's 0 mod 9. So 10 has residue 1 modulo 9. And that means that any power of 10 also has residue 1 modulo 9. Which means that x is equal to 1 to the n times x to the x sub n plus 1 to the n minus 1 times x n minus 1, and so on, modulo 9. So it's just equal to the sum of its digits, modulo 9. So what does that mean? X is equal to the sum of its digits. Yeah, so if one of them is divisible, if one side of this is equal to 0 mod 9, then the other side is as well. So if x is equal to 0 mod 9, i.e. it's divisible by 9, then the sum of its digits is also 0 mod 9, and it's also divisible by 9. The other way around, if the sum of the digits is divisible by 9, then so is x. So this goes both ways, if and only if. If x is divisible by 9, then the sum of its digits is as well. If the sum of its digits is divisible by 9, then x is also divisible by 9. Question, where does 10 to the x equals 1 to the, 10 to the k equals 1 to the k come from? So 10 is equal to 1 modulo 9, which means any power of 10 is equal to the same power of 1 modulo 9. And 1 to the k is just equal to 1. And so we're substituting that into here, where we have powers of 10, we can turn them into powers of 1 modulo 9. This is just a really fast way to prove this divisibility result. Okay, let's finally look at division in modular arithmetic and then prove the problem that we saw at the beginning. So we saw that addition and subtraction and multiplication work nicely. Division isn't quite as nice, but it's still pretty nice. If you want to divide, you're going to hope that the things you're dividing are already divisible by what you're dividing by, because we're working with integers here. So we don't want to have any things like 3 divided by 2. Or at least it's more complex when you're doing that. It is possible. But suppose you have a times x is congruent to a times y mod m. Then you know that x is congruent to y mod m if the integer a is relatively prime to m. Why is this true? Well, if ax is equal to ay mod m, then ax and ay differ by some multiple of m, cm. Now, if a is relatively prime to m, then c must be divisible by a, because there's no part of a that's going into the m here. All of the a over on this side must be from the c. That means that c over a is some integer, so x minus y is c over a times m, which is another multiple of m, so x is equal to y mod m. Some examples of this. 24 is equal to 2 mod 11. So I can divide both sides by 2 because 2 and 11 are relatively prime. So 12 is equal to 1 mod 11, which is true. Here's an example of why you don't want to do it unless the thing you're dividing by is relatively prime with a modulus. It's the thing in the parentheses here. If 12 is congruent to 2 mod 10, we could divide by 2 or try dividing by 2. But if we tried dividing by 2, then we would get 6 is congruent to 1 mod 10. Oops. 6 and 1 definitely do not differ by a multiple of 10. What they do differ by is a multiple of 5, which is 10 divided by 2. I'll let you think about what happens if you try to divide by some a that isn't relatively prime. You can still do it, but the modulus is going to change. 10 is in this case going to change to 5. Any questions about this? And then we will solve the problem at the start of lecture. Okay. Prove that n to the 7 minus n is divisible by 42 for every integer n. There's a really good suggestion of factoring n to the 7 minus n. We can factor it in a really nice way. Actually, we talked about that last class. I wasn't going to do it that way, but I'm sure you could do it in a really nice way. There is another way that you can do this if you know what's called Fermat's little theorem. I'm not going to talk about Fermat's little theorem, but if you are curious, you can go look it up. So how could we quickly prove that something is divisible by 42? Or what would be a way to prove that something's divisible by 42? We could show that it's 0 mod 42. That would absolutely be something we could do. Another thing we could do is just so it's divisible by all the divisors of 42. Both are perfectly reasonable approaches. I'm going to take the approach of 42 is equal to 2 times 3 times 7. So we could prove that it's divisible by 2 and also by 3 and also by 7. Why is n to the 7 minus n divisible by 2? For any n. Yeah, we can check cases. What are the cases? Yeah, the odd and even cases. Now, we've thought a lot about odd and even cases when we're thinking about divisibility by 2. What we're actually thinking about is different residues, mod 2. So odd is residue 1 mod 2, even is residue 0 mod 2. So since n is either 0 or 1, we can check both cases. 0 to the 7 minus 0 is just 0. 1 to the 7 minus 1 is just 0 as well. We can do the same thing for 3. N is equal to 0, 1, or 2 mod 3, and we can just check all 3 cases. 0, 0, and in this case it's a little bit more complicated. 2 to the 7 minus 2 is 126, but that's a multiple of 3, so it's 0. Now for 7, we can do the same thing, again checking cases, but there are some ways to simplify it. So I just sort of wanted to walk through it just to check, just to show you how I would do it a little bit faster. So for 7, we have 6. We have 0 plus 6 other possible remainders or residues modulo 7. 7 total residues modulo 7. So we can check the first ones pretty easily. 0, 0, 126, which is a multiple of 7. And then this one. This is a bit more complicated. I didn't really want to work out what 3 to the 7 is. So I said, OK, well, 3 to the 7 is 9 to the 3 times 3. It's just 3 squared cubed times 3. Now 9 to the 3, I can quickly simplify that 9. 9, I'm working modulo 7. 9 is just 2. So it's 2 cubed times 3 minus 3. I can calculate that a lot more easily than 9 cubed. So I just have 8 times 3 minus 3. 21, that's a multiple of 7. Great. Now what do I do for the others? 4, 5, and 6. I could do more of these calculations, and it wouldn't take very long. But indeed, we don't have to check those, because 4 is the negative of 3 modulo 7. So we can write 4 to the 7 as negative 3 to the 7. And 4 is just negative 3 here. So we have n to the 7 minus n, changing that to negative of negative n. So this is just the negative of 3 to the 7 minus 3. We know that 3 to the 7 minus 3 is just 0. So 4 works. We don't even have to do any calculation. And likewise, 5, the negatives come out. And 6, the negatives come out as well, because 5 is the negative of 2 and 6 is the negative of 1. That means that all the possible residues modulo 7 work. And therefore, n to the 7 must be divisible by 2, always, 3, always, and 7, always. And putting it all together, that's meaning that it is divisible by 42. I'll stick around for a few minutes to answer questions. Next time, we will be discussing combinatorics. Thanks, everyone.